Hello. Welcome to the final presentation for the Optical Beacon Tracker for Optical Wireless Communication by Group 4, sponsored by the Night Vision Lab.
Group 4 is comprised of Seth Johnson, Photonic Science and Engineering major, Blake Baez, Computer Engineering major, and myself, Raymond Laudis, Electrical Engineering major.
This project is sponsored by the Night Vision Lab. The Night Vision Lab is a research group at Creel at UCF with projects going on in subjects such as metasurface aberration correctors, vision-based navigation, and sensing technologies from small UASs. While optical wireless communications have existed for decades, clear communications requires precise alignment which is difficult to maintain whilst mobile. The goal of this project is to build a device that can track an optical beacon while both the receiver and the beacon are mobile.
The basic goals for our project is to create a beacon with enough power and divergence to be detected up to 3 meters away while indoors. Our advanced goal is to track the beacon up to 1 kilometer away while outdoors. And our stretch goal is to be able to track the beacon up to 10 kilometers away in ideal weather conditions and transmit and decode a simple signal like an SOS from the beacon.
In order to meet our goals, we have to accomplish these project objectives. We must calculate the required optical output power for the beacon to be detectable by the receiver.
The overall project is a two-part system made up of the receiver and the beacon. On the receiver system, there are motors attached to photodetectors. On the beacon system, there are illuminators attached to the motors. Both will be able to follow each other while mobile by the end of this project.
At a given distance. We must design the focusing, diverging, and collimating lens system on the beacon and receiver. We also must design the PCBs for the beacon receiver. Design a power supply for the beacon and receiver respectively, capable of driving the light sources and gimbals/DC motors, as well as biasing the photodiodes. Lastly, we must create an algorithm that enables the gimbals to use outputs from the QPD, GPS, and IMU.
This is our hardware block diagram, where we'll be using GPS, telemetry, and IMU modules with an ESP32. We will be regulating the voltage from a 22.8 LiPo battery, and we will be modulating the LED array and laser diode. However, one thing is different in our actual project is that we, instead of using a solid-state relay, we have used pulse width modulation using MOSFET switching. And instead of using a gimbal on the receiver side, we've had to also downgrade to servo motors. However, everything else is primarily the same. Although our hardware block diagram is a bit out of date, there are some concepts that we are still implementing currently, such as the GPS telemetry, IMU, and regulators. What has changed, however, is instead of a solid-state relay, we've gone with a pulse width modulation driver.
For calculating the incident power upon the receiver from the beacon, we will assume the worst possible divergence allowed in our specifications, as well as the formulas on the left. On the right, we can show the calculations for the incident power at a given distance with our worst possible divergence. These values for P-ins and P-out will be relevant when choosing our photodetectors and our illuminators. For a single-cell photodetector, we're using the Thorlabs FGA015 indium gallium arsenide photodiode. We chose this because of its cheap cost but still satisfactory specifications. Our other photodetector is more unique, the Spot-9D-0. It is a quadrant photodiode with a hole cut into the center, which will allow us to couple a fiber optic cable inside. This fiber optic cable will then connect to the single-cell FGA015 listed in the previous slide. Based on our earlier calculations, the beacon must output a minimum of 164 milliwatts at 850 nanometers and 450 milliwatts at 1550 nanometers. For our 1550 nanometer laser diode, we're using the CVLL350-90. We chose this for its high output power, relatively low threshold current compared to other high power diodes, and its cheaper cost for the higher output power. For our 850 nanometer illuminator, we are using the SFH4258S LED. We chose this illuminator because of its small viewing angle and acceptable driving current. We will put these in a 25 LED array, which will give us a total amount of power of 535 milliwatts within the 30-degree cone.
For our MCU selection, we went with the ESP32S3 Mini. We found when we were prototyping with the ESP32, we were coming quite close to the flash memory limit, about 92 to 93%. The S3 Mini was also slightly cheaper when creating our MCU boards, so it became the ultimate deciding factor.
Optic fiber and then expanded upon exiting the fiber and passes through a dichroic mirror and reaches the diverging lens. The 850 nanometer LED array passes through a high grit diffuser plate and then is then collimated and reflects off of the dichroic mirror into the diverging lens. On the receiver system, which is on the left, there is a simple condenser lens which passes both light sources onto and into the quadrant photodiode. A 850 nanometer filter with a hole cut into the center will allow the 1550 nanometer light to hit the quadrant photodiode and allow the 1550 nanometer light to pass through into the fiber and onto the single cell photodiode. For the design of this project, we'll start by referring to the optical diagram. On the right, it consists of the beacon system, which has a 1550 nanometer laser diode, which is coupled into an
Here we have the three PCBs currently implemented in our project. The receiver PCB features a quad cell photodiode and operational amplifiers to read out the signal and send it to the MCU for further analysis. The MCU PCB features the ESP32S3 Mini, as previously mentioned. It also features a temperature and moisture sensor to let us know whenever we have thermal issues. And the last one is the LED array PCB, which houses all 25 of our near-infrared LEDs. Heat sinks would have to be applied to the LED array in order to maintain correct thermals. Unfortunately, our PSU was unable to make the cut as the board layout for the LMQ61460 buck regulator was very sensitive and did not fire up as designed. Here are the three PCBs currently implemented in our project. The first is the receiver PCB, which features the QPD and operational amplifiers. The operational amplifiers take the signal from the QPD and send it to the MCU for further analysis. The MCU PCB features the ESP32S3 Mini, as previously mentioned. It also features a thermal and moisture sensor to let us know if our project is in danger. The last one is the LED array PCB, which houses the 25 near-infrared LEDs, also previously mentioned. Heat sinks had to be applied to the LED PCB to compensate for the extreme thermals. Furthermore, our fourth PCB was a power supply unit, which didn't make the cut based on board layouts. The LMQ61460 proved very difficult and sensitive to the board layout.
Software selection and design. Here is a software diagram that follows the general logic of our code. Programming language. Out of the top 4 picks, C, Java, Python, and C++, we ultimately chose C. The system that we are developing is essentially a soft RTS, or real-time system. It is imperative that our performance meets certain standards, but with minimal errors. That is so that the communication part of this project can be established and held. For C, memory control allows low level, performance is high, and has great support with plenty of libraries that we have used. Key concepts in algorithms and system control. In this project's code, we used search algorithm, an alignment algorithm, and we applied control theory as well as signal processing. For the alignment algorithm, there were 2 considerations. conical alignment, and radial alignment. Conical alignment involves adjusting the alignment of two systems or components by rotating one of them around an axis in a conical pattern until optimal alignment is achieved. Radial alignment involves moving or adjusting the alignment of a system radially outward or inward from its central point, typically along a straight line in different directions. We decided to use conical alignment for this project because of its efficiency and likelihood of evenly saturating multiple quadrants of the QPT at once is unlikely. Detecting current from one quadrant and narrowing down the range with the tilt and pan motors at the same time is much more efficient. Here we have a graph summarizing some features of the conical and radial alignment algorithms. For search algorithm, the two main considerations was golden section search and spiral search. Golden section search starts with an interval and evaluates the function at 2 points within the interval, spaced according to the golden ratio. Then you shrink the interval to discard the suboptimal side. The spiral search searches for the optimum by moving in an outward or inward spiral pattern from a central point. We ultimately chose the spiral search. Although at first appearances it seems less efficient and not ideal for this project, it is quite the opposite. It is just as efficient, if not more efficient, in certain scenarios, as well as more precise than golden section search. The downside is that it can be computationally expensive, but that's why we chose the ESP32S3 chip. Another key mention is the spiral search is efficient enough while also being more precise, as we mentioned before, which can make up for the inaccuracies of the IMU and GPS that we are currently using. The GPS can be off as much as by 3 meters or sometimes more, and the IMU azimuth can be off by as much as 20 degrees for various reasons. Such reasons can include some interference or an issue with initializing from the library. Control theory. For control theory, we will be implementing a Kalman filter. It is a mathematical algorithm used to estimate the state of a dynamic system from noisy measurements. A Kalman filter was used to combine GPS and IMU data to estimate position better. It specifically allowed the tracker and gimbal to track each other without using a search algorithm to search for a signal in a wide range. It allowed us to pinpoint an area with accuracy as good as the GPS and IMU can provide. Signal processing. Signal processing was used to make up for the shortcomings in the modules that were purchased backup to this project. As mentioned before, in control theory, the IMU needed smoothing signals as well as a library implemented to allegedly help the noise interference and refining the data coming in to eliminate IMU drift. IMU calibration is also an important part in this. These next two slides will show the receiver sequence diagram and then the transmitter sequence diagram. Both sequence diagrams show the logic path that each ESP32 S3 must take in order to complete the tracking system. Graphic user interface. For this project, we went through multiple graphic user interfaces, starting with several LCD screens. They all seem to pose an issue communicating with the ESP32 dev kit specifically. So we moved on to a website or SSHID based approach. All the necessary data that the user would need or want to see will be displayed on this GUI. Such things include the azimuth and GPS coordinates of the transmitter and receiver. The GUI also allows to start and stop the program whenever the user pleases and wherever. This is because it establishes a DNS and connects over Wi-Fi. So as long as the user is connected to the same local internet, they must simply input the IP address that is put out in the serial monitor when running the code. In this slide, we can see what the graphic user interface will look like. Bottom is a start-stop. The status will tell you if it's stopped or if the code is continuing. The graph test is just monitoring over time. Longitude and latitude, self-explanatory, as well as the azimuth. In the millis area is the milliseconds. That will be our response time. The time will be based off of the difference of when a signal is detected and when the signal is sent to the motors to move.
Here's the major expenses of this project so far. Most items were paid for by the Night Vision Lab, but other items, such as our LoRa and GPS GMV2, were paid for by ourselves, as well as certain experimental materials. The budget for this project was provided by our sponsor, the Night Vision Lab. A few items, such as our motors and GPS components, were paid for out of pocket.
On this slide, we feature our assembled prototypes. On the left is our receiver prototype, which features our quad cell photodiode, collimator lenses, and regulators, as well as an ESP32, GPS module, and IMU. All of these are currently wired together with 18, 22, and 24 gauge wires to compensate for the different currents flowing through them. In this photo, we are still implementing our ESP32 Room 2 dev board. However, for our final project, we will be using the S3 as previously mentioned. On the right side, we have a similar setup, only instead of the QPD, we are using the LED array and laser diode. In the photo, you can notice at the bottom left-hand corner are MOSFET switches, and at the top right-hand corner are voltage regulators. We were using 3 of those voltage regulators to power the 3 series of LEDs in our array and setting them to a constant current of 100 milliamps. This, in addition to the MOSFET switches, allow us to modulate our LED array and remain at a safe current level. Currently, all the wiring is done with using wire nuts, but will be replaced with heat shrink as we go into our final demo. Furthermore, when assembling both the prototypes, we found that having the GPS and IMU and the LoRa separated across the base and on top of the apertures helps us spread out the signal and not interfere with one another. In conclusion, although there are still some minor tweaks to be made, this is fundamentally what will be shown in our final demo.
Work distribution. Seth Johnson will be working on the optical design, optoelectronic hardware selection, and physically assembling the beacon and receiver with Raymond. This also includes 3D printing and assembling. Me, Blake Baez, will deal with all the software design, the MCU, GPS, LoRa, and IMU selection, as well as designing and maintaining the website. Raymond Ludis is in charge of the electrical and PCB design. He will also be dealing with the electrical hardware selection. He will also be physically assembling the beacon and receiver with Seth.